This is problem 12 of the 2005 Further Maths exam, paper 1, summer. The curve gamma, which has equation y equals ax squared plus bx plus c divided by x squared plus px plus q, has asymptotes x equals 1, x equals 4, and y equals 2. Find the values of a, p, and q. So immediately we know that a is equal to 2, because it has a horizontal asymptote y equals 2. So a equals 2. And then if it has vertical asymptotes x equals 1 and x equals 4, that would imply that x minus 1 times x minus 4 is equal to x squared plus bx plus q. And if we expand that out, we get x squared minus 5x plus 4. So that would mean that p is equal to negative 5 and q is equal to 4. So just rewriting this thing, we have 2x squared plus bx plus c divided by x squared minus 5x plus 4. Next up, we are told that gamma has a stationary point at x equals 2, and then we're asked to find the value of c. So we should differentiate it. Y prime is equal to 4x plus b times x squared minus 5x plus 4 minus 2x squared plus bx plus c times 2x minus 5. And then the whole thing is divided by the one on the bottom squared. X squared minus 5x plus 4 squared. And then this should be equal to 0 when x is equal to 2. Since we're going to need it again anyway, let's just go ahead and expand this derivative out completely. So for this thing to equal 0, we need 4x cubed minus 20x squared plus 16x plus bx squared minus 5bx plus 4b, and then minus 4x squared plus 2bx, 4x cubed plus 2bx squared, and then plus 2cx, and then minus 10x squared minus 5bx minus 5c. Simplifying it down, we got negative, so we got b minus 20, lots of x squared here, and then 16 minus 5b, lots of x, and then 4b as the constant, and then inside the brackets we've got 2b minus 10, x squareds, and then 2c minus 5b, lots of x, and then just negative 5c as the constant. Okay, now we got b minus 20x squareds minus 2b minus 10x squareds. So we've got negative b minus, looks like minus 10, lots of x squared. And we've got Gosh, looks like the b's are going to cancel here. So it's just going to be 16 minus 2c lots of x. And then just plus 4b plus 5c. And this should equal 0. Okay, so that is the derivative equal to 0. So all the values of x which make this derivative equal to 0 is where the stationary points are. And we're told that there is a stationary point when x equals 2. So if we substitute that in, we get negative 4b minus 40 plus 32 minus 4c plus 4b plus 5c equals 0. And we see the b's cancel out as they should. And then simplifying it down, we get negative 8 plus c equals 0. And so that tells us that c is equal to 8. Okay, so that takes care of part I. And then part II asks us to show that if b does not equal negative 10, then gamma has exactly 2 stationary points. And luckily for us, we've done all the hard work already, because we found the derivative. So the values of x which solve, just to make it prettier, I'm going to move everything to the other side. So b plus 10 times x squared plus 2c minus 16x, and then minus 4b plus 5c equals 0. So there are stationary points at any value of x which solve this equation here. Gosh, what am I doing? We already found that c equals 8, and so this, well, 2 times 8 is 16, minus 16 is 0, so we don't even need to worry about the middle part. So it's just b plus 10x squared, and then minus 4b plus 40 equals 0. And then we just get that x squared is equal to 4b plus 40 divided by b plus 10. And we're assuming that b does not equal negative 10. So we can just divide the top and the bottom by b plus 10. And we just get 4. So there are stationary points when x equals 2 or negative 2. And part III asks us to draw a sketch of the curve in the case where b equals negative 6. So just a reminder, we found that c was equal to 8. So we can make this an 8. And then if b equals negative 6, so that's our function there. So there's what we have to do. And we've worked out already most of the information that we need. Something else we should probably work out is what is the range of this function. And so to that end, we do our usual technique of multiplying both sides by the denominator, and then subtracting, and then finding where is the discriminant greater than or equal to 0. So we got y minus 2x squared, and then plus 6 minus 5y, lots of x, and then plus 4y minus 8 should equal 0, and then delta is equal to 6 minus 5y squared minus 4 times y minus 2 times 4y minus 8. And we need this to be greater than or equal to 0. And just to save a bit of time, I did all the expansion without making you watch. And then we get to 9y squared plus 4y minus 28 needs to be greater than or equal to 0. And 9y squared plus 4y minus 28 equals 0 if and only if we have y equals negative 2 or y equals 14 over 9. And then just drawing the parabola, we can see that this thing is bigger than 0 or bigger than or equal to 0 if y is greater than or equal to 14 over 9 or less than or equal to negative 2. And earlier on we calculated that we have stationary points for x equals plus or minus 2 as long as b didn't equal negative 10, which it doesn't in this case. And so, well, putting those values in, for example, if we put in x equals negative 2, we get 28 divided by 18, which is the same as 14 over 9. So 14 over 9 goes with x equals negative 2. And if we put in x equals positive 2, we get that y is equal to negative 2 in this function. So clearly we have a minimum, a local minimum, at the point x equals negative 2, y equals 14 over 9. And we have a local maximum at the point x equals positive 2, y equals negative 2. Okay, so after compiling all the information that we have from what we've worked out or just looking at the curve, we're ready to sketch this thing. And since the y-intercept is clearly when y equals 2, because that's what we get when x is 0, we can see that it also intercepts its horizontal asymptote at that point. So let's go ahead and work this thing out. So first, drawing in the horizontal asymptote, y equals 2. And then the vertical asymptotes, x equals 1. So x equals 1, or x equals 4. So 2, 3, and 4. Damn, I missed it. X equals 4. Alright. And now we know that, what else do we know? We know that there's no x-intercepts, and we know that we have a y-intercept when y is equal to 2. So we're going through this point here. And we know that we have a local maximum when x is equal to 2 and y is equal to negative 2. So it's going to be that point there. So this is, just label it to be clear, to negative 2. And we also have a local minimum when x is equal to negative 2, so negative 1, negative 2, and y is equal to 14 over 9, which is a little bit bigger than 1, which is here. And then putting all this information together, it is extremely easy to get the shape of the graph, because we know there are no x-intercepts, we have the maximum and minimum points. I guess I better label what the coordinates are. Negative 2 and 14 over 9. 14 over 9. And then you can check by setting it equal to 2 that it's only going to intercept the horizontal asymptote at this point here. So it can't come through the curve or anything. And it also can't, like if it cut the curve again or something, then it would have to turn around again. And so that would create another maximum point. So we can't have it for multiple reasons there. So it forces the shape of the curve over here to look like this. And then it, oops, minimums out. I should probably draw that again. So it comes down, and then it reaches its minimum here, and then it starts coming back up again, and then kind of snakes towards the horizontal asymptote y equals 2. So you should make it clear that the minimum point is negative 2, 14 over 9. Luckily, this isn't an art contest, or I feel like a few of us would be in trouble. A few of us would probably be pretty happy if it was, though. Okay, and now for this point here, because we have no x-intercepts and we have vertical asymptotes here and here, and the function is continuous between those vertical asymptotes, it has to look like this. It has to max out at this point, and then just come down and then go towards the line x equals 4. And finally, no x-intercepts, vertical asymptote here, horizontal asymptote here, no more maximums or minimums or interceptions with the asymptote, so that forces the shape of this last part to be this. And then we're done.